Here we are going to fully analyze this trigonometric function by finding any extreme points, both local and absolute, and points of inflection. So we're going to expose everything we know about this function. That means we did things like find extreme values. You could use the first derivative test for extrema there, stuff from section 4.3, and inflection points use a second derivative test for concavity there using section 4.4, or we could see if possibly we can merge the two tests and use the second derivative test for both concavity and changes of concavity, points of inflection, and extreme values. So the first thing I'm going to do is just break it up into two easy pieces. First, we'll test for extreme values. We'll use the first derivative test for that, and we just want to find max and minimum values. So remember, the first step, we're to find critical points of the first derivative. So the first derivative is the square root of 3 plus 2 sine of x, because the derivative of cosine is negative sine, and we want to know where that equals 0 or doesn't exist. Remember, just keep that in the back of your mind. This guy always exists. Sine is continuous from 0 to 2 pi, so we don't have any points where it might not. So if we solve for sine, we need to know where sine of x equals the negative square root of 3 over 2. I subtract the rad 3 and then divide by 2. So now we need to answer this trig function, or this trig equation, solve it. Where does the sine equal negative square root of 3 over 2? Sine of theta is the y value on the unit circle, and we need to know where he's negative square root of 3 over 2. So y values are negative down here below the x-axis, and we need the square root of 3 over 2. So that's the deeper y values, right? Larger. So there's two places on the unit circle where that happens, and we can find this point. If you remember that the ugly values of the sine happen at pi over 3. That's just what I remember. So that means that x is pi over 3 past pi, which would be 4 pi over 3, and then one more pi over 3 around this way, almost to 2 pi. So 2 pi over 3, 2 pi's in the over 3 would be 6 pi over 3, but we don't quite have that many, so we have 5. We have these two solutions, 4 pi over 3 and 5 pi over 3, where the sine of x is negative square root of 3 over 2, or the first derivative equals 0. So those are our critical points to test the interval. Step 2, divide the interval by the critical points and test the first derivative. The interval we're concerned about is 0 to 2 pi. The critical points of the first derivative are 4 pi over 3 and 5 pi over 3. We want to test the first derivative for extreme values, increasing, decreasing. So step 3 was to test, and we're going to test the first derivative, y prime, square root of 3 plus 2 sine x. So some number between 0 and 4 pi over 3, if I reference my my circle up here, I can find that I have two nice values to test this first derivative at. Those are pi over 2 and pi. At pi, sine is 0, so that's even better. So I'm going to test y prime of pi. That's the square root of 3, right? Because the sine of pi is 0. So that's a positive value. That means that the function is increasing on this interval. Now we have to test some number, some value between 4 pi over 3 and 5 pi over 3. Remember our circle here, it's getting kind of jumbled up. A nice value to test there would be 3 pi over 2, that quadrantal angle, the negative y-axis. The sine value down there is negative 1, so now we have the square root of 3 plus 2 times negative 1, or the square root of 3 minus 2. And this value is negative. I can pull out my calculator and find out how negative, but I know that it's negative because the square root of 3 is just 1 point something, and 2 is larger than 1 point something, so when I take away 2, I'll get a negative value. That means the function's decreasing on this interval because it's negative. Then next interval, test a point between 5 pi over 3 and 2 pi. We have two nice choices, a pi over 4 option and a pi over 6 option. I like the pi over 6 because sine of pi over 6 is a half. So let's try pi's over 6. Now we want to be almost to 2 pi. 2 pi in terms of pi over 6 would be 12, but we're not quite there. So we must be at 11 pi over 6. So that's the square root of 3 plus 2 times the sine of 11 pi over 6. And 11 pi over 6 is negative half. That's the square root of 3 plus 2 times negative 1/2. That's the y value is negative there. So the square root of 3 minus 1, that's a positive value because the square root of 3 is 1 point something, take away 1. So now I know that the function is increasing on that interval as well. So that's the third step. Fourth step was to make the decision. Where are the maximum and minimum values? Well, we can see that we have a max at 4 pi over 3 and a minimum at 5 pi over 3 because of the behavior of the function, increasing to decreasing, decreasing to increasing. And we also can consider the endpoints of this closed interval. At 2 pi, we're increasing until we get to 2 pi. So that means that the value, whatever value of the function has at 2 pi must be a maximum because it's taller than all the stuff around it. And at 0, we must have a minimum. So now that we have these max and min, we have to decide which one's absolute. Like you could say they're all relative, max and min, so whatever we've labeled. But which ones are absolute? To answer that question, excuse me, we need to evaluate the original function at those points so we can see what value we get. So let's consider the maximums first. The y value at the first max, 4 pi over 3, is the square root of 3 plus 2 sine 4 pi over 3. That's the square root of 3 plus 2 times the sine of 4 pi over 3. No, the cosine, original function. Excuse me, I was referring to the first derivative. Let me label that. Use the original function. Y is the square root of 3x minus 2 cosines of x. That changes this. Y of 4 pi over 3, square root of 3 times 4 pi over 3 minus 2 times the cosine of 4 pi over 3. So that's not very pretty at all. 4 pi over the square root of 3, if you want to combine those powers of 3, minus 2, and the cosine of 4 pi over 3 is a negative value. It's in the third quadrant. And cosines of pi over 3 are half, so negative 2 times negative 1/2. So that's the 4 pi over the square root of 3 plus 1. Not an easy number to evaluate. Let's see what the other value is. Maybe we can compare it. The original function at the next maximum value, which is 2 pi, is the square root of 3 times 2 pi minus 2 cosines of 2 pi. So we have 2 square roots of 3 pi, and the cosine of 2 pi is 1, so minus 2. I'm not too sure. I can't compare these two together. Sometimes you can if one turns out to be a nice easy number like pi or 0 and one's positive, but not in this case. So let's pull out our handy dandy calculator and see what we get when we evaluate these. You can use these values that we simplified, or you could go all the way back to the original function, whatever makes you feel more comfortable. Square root of 3 times 4 pi over 3 minus 2 cosine of 4 . pi over 3. Make sure your calculator's in radians, and she is, so I can evaluate this expression. 8.255. And then I need to change it, evaluate the same function, but now at 2 pi. So you could go back up and grab it if your calculator has that function. I'm going to replace the 4 with a 2 and delete the denominator. .88. That's a close call. Good thing I didn't try to reason through that one. 8.2. That would be smaller than 8.8, so this guy's the winner. He's the absolute max. And 8.2 is simply a relative max. So let's evaluate the minimums. Same process, use the original function to compare the y values for the two minimums. The first minimum is 0, I like that number. 3 times 0, square root of 3 times 0 minus 2 times the cosine of 0 is 0 minus 2, because cosine of 0 is 1, so we get a y value of negative 2. And what's the value of the function at the other minimum, 5 pi over 3? That's the square root of 3 times 5 pi over 3 minus 2 cosines of 5 pi over 3. So 5 pi over the square root of 3 minus 2 times the cosine of 5 pi over 3. Cosines of 5 pi over 3's are halves, like pi's over 3 make half in cosine. 5 pi over 3 is in the fourth quadrant. This is a positive 1/2 where the x value is positive, so we have 5 pi over the square root of 3 minus 1. Fortunately, I don't have the capacity this morning to think about what that means to us in numbers, so while the calculator's already out, we might as well use him. You could calculate this or that. I already have this thing typed in, so I'll just change all the 4's to 5's. And we get 8.06. Okay, so 8 is larger than negative 2. That means negative 2 is the absolute min. And 8.06 is a relative minimum. So now we can finally label all the extremum of the function. We have an absolute maximum, also an absolute minimum, a relative maximum, and a relative minimum. Now check with your instructor. For how they would like this written. I'm happy to say just where the values occur. So the absolute maximum of 8.8, that's the biggest of y value the function gets, happens at 2 pi. So I'm happy to say that the absolute maximum is at x equals 2 pi. The absolute minimum is at y equals 0, or x equals 0. The relative maximum happens when x equals 4 pi over 3, and we get a relative minimum at x equals 5 pi over 3. There are schools of thought that might say the absolute maximum value is 8.88, and that happens at x equals 2 pi. The minimum value is negative 2, and that happens at x equals 0. Or you might see them as coordinate points, 2 pi, 8.88, or that exact expression we used before, make it to be exact, and then 0, negative 2 is the absolute minimum. Then when we examine the relative extremum, we might also list the absolute. I'm happy if you just list the ones that are strictly relative, but you check your books, check your instructor, see how they would like it, because x equals 2 pi is not only an absolute maximum, but also relative maximum, since he's higher or taller or has a larger value than all of the points around it in his neighborhood. So by the definition, they really are relative values, relative extreme values as well. So that's the first test. All we did there was test for extreme values. Now we have to go back and remember that we're also asked for inflection points. So let's do that in section 2. Test for points of inflection. The steps are similar, but now we're going to use the second derivative. So we already have y prime over there, and we'll make up y double prime. Derivative of sine is cosine, so we get 2 cosine x. We care where that second derivative equals 0 or doesn't exist. Cosine's continuous function from 0 to 2 pi, so we don't have this, but we always keep it in mind. Now the question is, where does the cosine of x equal 0? Hopefully you're getting a feel for these trigonometric functions because they will not go away. Cosine equals 0. If you remember that the cosine of theta is equal to the x value, and x equals 0 here and here. And those two angles are pi over 2 and 3 pi over 2. So we have two solutions, or two critical points of this second derivative, pi over 2, 3 pi over 2. Second, just like we did with the first derivative test, we're going to test this interval, divide it up, but test from 0 to 2 pi the second derivative. Now, the critical points of the second derivative were pi over 2 and 3 pi over 2. We're interested to know if these are actually points of inflection of the function. So now, instead of testing the first derivative for increasing, decreasing intervals, we're going to test the second derivative, 2 times the cosine of x, to investigate the concavity of the function. From 0 to pi over 2, we have to pick some point there to test, so you get any of the options 3, 4, or 6 in the denominator. If I'm going to evaluate cosine, I'd rather do 3, so let's check y double prime at pi over 3. That's 2 times the cosine of pi over 3, and the cosine of pi over 3 is a half, so this value is 1, namely positive. That's what's important for us. Positive means that this function is concave up on this interval. Then we'll test between pi over 2 and 3 pi over 2. Nice point there is pi. 2 times the cosine of pi is negative 2. Since the cosine of pi is negative 1, that means that this second derivative is negative. That's the important thing. Concave down. And we'll check the second derivative between 3 pi over 2 and 2 pi. So that's any of these three angles which are close to 2 pi. Again, I like the ones where we have pi over 3 for cosine. That's where cosine's a half. Almost to 2 pi, and 2 pi written over 3 would have been 6. So we have 5 pi over 3. The cosine of 5 pi over 3 is positive half. So 2 times the cosine of 5 pi over 3 is 1. So this second derivative is positive. That's the important part, concave up on this interval. Fourth option, or fourth step, is to decide if we have any points of inflection, and in fact we do. We have points of inflection each time we change concavity, so that happens at pi over 2 and 3 pi over 2. Points of inflection occur at the points x equals pi over 2 and 3 pi over 2. So now we've answered all the questions, right? We found the extreme values, and we also found the inflection points. Points of inflection, pi over 2, 3 pi over 2. Extreme values of the function, absolute maximums, minimums, relative maximums, and minimums as well in that scribble. So you can put together these two pictures to make a graph of the function. Now you know the increasing and the decreasing intervals, and also the concavity. Given this depiction of what's going on as far as increasing, decreasing, and the concavity, up and down, we can sketch a graph of this function from 0 to 2 pi. So here's the y-axis and the x-axis. This is obviously 0. Here is 2 pi. So halfway through would be pi. Halfway between there's pi over 2. halfway between here, 3 pi over 2. It might help you to plot the maximum and minimum values. So at 2 pi, we're all the way up at, we found an approximation of 8. So at 2 pi, the absolute maximum value was 8.8, even bigger than 8. So plot this point, absolute maximum. The absolute minimum value was -2 at 0, so this scales 4. -2 would be right here at 0. Then we have relative extreme values, max and minimums, that were So what I like to do are plot these extreme values, max and mins. So we have an absolute min down here, relative max, absolute max at 2 pi, and then a relative min at 5 pi over 3. So once we get those points plotted, we can look at these points of inflection. Somewhere along where x equals pi over 2, we have a point of inflection, and at 3 pi over 2, there's a point of inflection. So I'm not particularly sure. I never went back and got the y values for those, but somewhere along that vertical line, we have to change concavity. Then down here, I'll indicate to myself what kind of concavity I need. Concave up first, then concave down, then concave up. So now I have to start the sketch. I start at 0, and I'm going up to this relative maximum, but to get there I need to be concave up first and not get any lower than 0, right? Concave up, but no lower than 0. And then I need to turn around and be concave down at pi over 2, but not get any higher than my maximum. So I kind of overshot that a little bit. Let me go back and sketch it a little better. Concave down, but not any higher than my maximum. So I'm slowly increasing to the max, and then I can be going back down. Now I can't do very much here, very flat, but still concave down. Then I turn around and be concave up across the point of inflection, and I'd be frustrated that the relative mins and maxes are not very far apart from each other, so it won't hurt my feeling to just adjust this relative minimum, which I think was at like 8.06 or something, and just pretend like that's 8.06 down there wherever I drew my line, because that's not very different than 8.2. Okay, so now I'm concave down to the min, still concave down, but now increasing to the maximum. So there I've met all the requirements and made this okay looking sketch of the graph where I have a point of inflection at pi over 2 and a point of inflection or a change in concavity at 3 pi over 2. If I wanted to, I could re-sketch it so it looked a little bit nicer, but this gets the point across.